So then let's move on to our next speaker, Guillaume Faye. He's going to talk about post-Newtonian calculations with xAct and xTensor.
Thank you. So I am very pleased to be here to celebrate the 20-year anniversary of the first xAct release. And I'm going to show how to do post-Newtonian calculations with this tool, xAct xTensor, which is something that people want to do very often. I have not designed any public package because I use my own formalism. It's very specific and it's always changing. There are new quantities to add and so on, but I can tell about the main ideas. They are very simple, nothing very complicated, and I use basic tools of xAct xTensor, but they are very powerful. So let us first initialize the session and load xAct xTensor. I will need a few constants, like Newton's constant, and the speed of light, the space dimension, and a small parameter, because actually I'm going to talk about post-Minkowskian expansion, which is a perturbative expansion in G, Newton's constant, and post-Newtonian expansion, which is a perturbative expansion in 1/c, the speed of light. So now I can describe the geometric environment. Here is the space-time manifold with Greek indices in d+1 dimension. I have flat metric eta associated with the derivative, which is a generic partial derivative. So I can evaluate that. It's done already. So I do the same for the space manifold with Latin indices. I have a time parameter, and I, of course, define a flat metric delta with also the partial derivative. And for instance, this is the metric, and of course, it does not depend on time. So let us move on and go to the gravitational field, which is regarded as a tensor field on the manifold endowed with a flat metric. I have only my partial derivative that is compatible with the metric, so I can put this parameter to false. And now two canonical recognize that the metric commutes with the partial derivative, and two partial derivatives commute. So no problem about that. Everything is flat. I introduce the Gothic metric notation. I have my perturbation, which is the deviation of the Gothic metric from the flat metric. It's also useful to have the usual metric perturbation, the stress energy tensor, whatever you need to do general relativity. And then I do the same definitions in d dimensions for just the space part. Also, the determinant is needed in d dimensions. I have some simplified notation for multi-time derivatives, as you can see here, because there are a lot of them. Okay, so now here is the relation between the Gothic metric and the perturbation h mu nu. This is our perturbation. Using the small parameter, I introduce a truncation command. For instance, here I truncate the square root of 1 plus h squared at order 10 in h. You see, so it works. So here, this is the post-Minkowskian order. I need to execute this piece also. And here, something quite important, it appears to help a lot in long calculations to eliminate dollar indices that appear explicitly in the index rules that are generated automatically. So I will have this command to do that. I have then the relations between the quantity I am interested in, the quantities, and h mu nu. And for instance, here I show the relation between the metric perturbation and h mu nu, just to show how it looks like. It depends on the space dimension d, of course. This is now the stress energy, pseudo stress energy tensor of Landau-Lifshitz, okay, in terms of the inverse metric, the Gothic metric, and so on. The left-hand side of Einstein equation is written in terms of the derivative of the third superpotential. So I define this superpotential here. Then combining those two things, I have the Einstein equations saying that this is equal to 0, this thing here. And now I use my rules to replace everything in terms of h, and I truncate at every step. And here is the final result. So the Einstein equations are there. But I need to consider most generally the right-hand side of the equations and in harmonic gauge. So here I define some rule for the gauge condition. Here I apply it to check it works. So you can see that here is an index on the derivative contracted with an index is h mu nu. And so I apply this rule and I truncate on my right-hand side of the equation. This is not yet the right-hand side. I need to remove a piece which belongs to the left-hand side, and then I obtain this tau mu nu tensor, which represents the right-hand side of Einstein equation in with some stress energy tensor T mu nu in terms of H, okay, the H perturbation. Very good. It's useful sometimes to remove T mu nu from this if we are outside the matter system. This object is of course symmetric, as you can check easily, and you can extract the quadratic part. For instance, this is the quartic part because you remember at some point I said that my order was 4. Okay, so I stopped at quartic order, but if I had slightly more time, I could show you easily to go to order 6. Here you have 31 terms in this quartic part of the source. Sometimes it's useful to unsymmetrize something which is symmetric. So I have a very simple command to do that. This means that when you have defined this unsymmetrized quantity, if you resymmetrize it, you will come back to the original quantity. And the gain is that you have less terms, and if you need complicated manipulations, this is useful. Now, of course, at the end, we want to do post-Newtonian calculation or multipolar expansions. So we need 3+1 splitting. So I define a time manifold. I need some rules saying how my tensor are noted in d dimension, space dimensions. So they are generated automatically for the tensors of interest. And then I use those rules in this simple code based on very simple and basic xTensor command. So for instance, up index or some pattern here, indices of, get indices of V bundle, trace dummy, which is very important here to trace on indices. So now I show an example. So I apply this command. Here I say that mu nu become just time indices. So this is the 0, 0 component. And I simplify a bit with this combination of two canonical put scalar and contract metric. I obtain this. This simplification can be defined in some arrange command. And here is an example on the 0i component. Very similar result, but with less parentheses, scalar parentheses. Okay. And finally, ij component of the source. So it takes slightly more time, but it's still very short. Here you have 341 components. Okay, so if I unsymmetrize it, I get less components, and then I can do further manipulations. I will focus later on the quadratic contribution. So I define the quadratic part of the source and move to the next section. So I am setting the space dimension to 3. And now I'm interested in multiple moments. So multiple moments parameterize the linear metric. So here is the mass type moment here. This is symmetric and trace-free. Similarly, I can define a current type moment. I define some radial variable, some other useful quantities. I mean, it's not very interesting. The angular part will be described by a vector, unit vector, depending on theta and phi of the spherical coordinates, pointing towards the field point. And actually, this vector can be multiplied with itself, a tensor product. to obtain a tensor of length of rank L involving n times the unit vector, and we call this NL with some multi-index. So this is defined here. This is very convenient. So for instance, it's a symmetric quantity. You can combine two NL tensors with themselves. If you contract indices, they disappear because of the unit property of NL, which is originally just one vector, unit vector. I will need some generic index to specify what multiple moments I am interested in. So this means that I am interested in the quadruple, mass quadruple, and the current quadruple. I call them moment 1 and moment 2, and I will use this later. I need more properties. So the multiple moments are trace-free. You can compute their derivatives. They are retarded quantities. So if you compute the space derivative, you obtain some time derivative here. You can, of course, compute the derivative of the angular quantities. Now, I am in the position to start more serious things. So this is the general definition of linear metric, but I truncate it at some order. Here it's 4. So I obtain the result explicitly at this order 4. This is 0, 0 component of H, 0 I component, and ij component. And I can check that the result obeys the vacuum Einstein equation, linearized. So the source is 0 here. We are in vacuum. Okay, so we expect to find 0, and the gauge conditions are satisfied. So now I will define some command that takes some quadratic expression and replaces there the metric by its expression in terms of the multiple moments, keeping only the 2 moments I have considered before, the current quadruple and the current and the mass quadruple. So here, for instance, in this particular source, there is no such interaction, but if I consider the square of this time derivative, the interaction is not non-zero. Okay, here I now can compute the source, and I can actually simplify it. The longest thing is the simplification. It takes a few seconds. So I think I will just show you the structure involving, here it's a scalar. So you see that scalar are there everywhere. You have epsilon Levi-Civita, the angular part, the radial part, and multiple moments. And just the interaction I have considered. But because when you do post-Newtonian calculation, you know in advance what interaction will contribute to a given order. So here I do the same for the other components of the source. So I will go faster. So you see the structure is similar, but now they are not scalar anymore. And you do the same for the ij component. So without waiting for evaluation, you see it takes about 20 seconds for this one, for instance. So I go to the next step, which consists in defining the symmetric trace-free part of this angular object NL I defined before. This is equivalent to spherical harmonics. I could as well use spherical harmonics, but because I use xTensor, I like to use the power of tensors. So here I define this object, here for instance with 1 index. Here you see it's really a symmetric object, hopefully when it will evaluate, and it's trace-free. Here it will take 23 seconds, even more perhaps now, if I evaluate this symmetrized product of metric, which I need to relate the n hat notation to the n tensor I introduced before. So this is quite long. I will not execute that. Instead, I have my own command that computes precisely the combination of deltas that are there in this particular symmetric combination. So I don't use symmetrize. Perhaps I could do it with manipulator, but here I don't even consider symmetries. I just generate the indices and I put them correctly in the way they appear in the formulae. And here it is very fast. Even with my slow computer, I generate this in a fraction of a second. And actually, I save the result in the command itself, which makes it even faster for further evaluation. Very good. So I can now define a command to transform. So here it's not very interesting, but to transform generally NL into its decomposition in STF quantities, STFN. I can do it in d dimensions actually. So here are the formula in d dimensions. Okay, it's quite fast. More explicitly without gamma functions here. Very good. Now I can do exactly the reverse and transform STFNL, NL hat, to decompose it in L and to write explicitly the expression. I will not show because it's a bit long. Here, if I use STF part, because it's not tuned to my specific notations and so on and symmetries, it will take 11 seconds while I have 2 less indices. For the equal number of indices, it will take quite a long time. So here, I can compare the 2 results. They are the same, but I will not do it due to the weakness of my computer. I come back to 3 dimensions. Now, I will quickly show you how to integrate these equations with xTensor. So actually, I want to apply box -1 operator. I need to define integrals, and in integrals, you need to say if you have an object like this, at what time, time being the integration parameter, you consider it. So those objects are constant, therefore, there is no need of argument. The dipole is 0 in our center mass frame, but if you consider quadrupoles, you can specify at which time you evaluate them and use them in some integral command. This integral does not evaluate anything. I mean, it's an inert integral defined with inert head that we discussed in earlier talks. So for instance, this is this inert integral applied to so this object, third derivative of the quadrupole, evaluated at this time, and time runs from 1 to infinity. It's not exactly time, it's almost time. And we have a log kernel. You can have constant objects in arguments. They go outside the arguments. Here, the angular dependence also goes outside. Okay, now I have also some commands to integrate using the box -1 operator and the tools I just introduced. I don't show the code. I have no time to do that. I just show how it works. So here it's very simple. Now you have some cutoff that appears. Another simple example, but here some integrals is generated and I need my integral notation. Okay, very good. I will skip this and go directly to the evaluation of this on my source. But first, I need to express my source in n hat, in terms of n hat, because the retarded command is defined only when you expand in spherical harmonics. So this is what I do here. So you see, it's similar compared to previous expressions, but now instead of n, I have n hat. I can apply this. Okay, I can print the result. Well, yeah, so it's a bit ugly. You have a lot of dollar indices, but it's computed. Okay. Yeah, it's quite long. Right, it was just to show you how bad it can be. If I apply to canonical, it does not work actually. I do it just for fun because why? Because in the integrals, one of the integrals is written here. You have complicated sums multiplied by the kernel. And so 2-canonical does not like sums like this put all together in one inert head. So what you have to do here is to expand what can be expanded here, but keeping the kernel intact, because otherwise the integral will be divergent. And then you replace the sum of the kernel by a fake sum. So I need to evaluate this to define my fake sum. Then this simple rule, and the rule fixes the problem. Here, this is the fake sum. It's not very visible. I should maybe improve the notation. Then I define an integral arrange, and now I can simplify my expression and integrate the 0, 0 component. I can show you quickly the 0i component here, and similarly, the ij component, it starts to be slightly long, 500 terms. Okay, very good. But I want to discuss the application of those ideas also to binary systems. So I reset my session because I'm going to load a package and there are notation incompatibilities. So I hope this time loading the package will not make any problem. No, it seems to work. So this is a package based on xTensor I designed notably with Sylvain Marsat many years ago. Okay, now let us go to the tensorial environment. So the field point is represented with the radius r and some unit vector. Okay, the particle positions are y1, y2, the velocities v1, v2. So this is the configuration space. You have the separation vector y1 minus y2, split into angular and radial dependence, and similarly for the separation between the field point and the body point. So you see always angular part and radial part. So anyway, so those are the notations, and now I can define the stress energy tensor components, the parametrization of the stress energy tensor for point particles. I need to redefine the metric in 3D. The metric is parameterized with many potentials. And I can show you just for fun the expression of the metric at 3pn in terms of those potentials. But then those potentials need to be replaced by their actual values. So, and those values are quite ugly, actually. So the variables are what they are. So unit vectors are unit vectors. You can simplify scalar products using relations with radii. Let's go to the core of this. You can differentiate 1 over r1, for instance. Okay. Second derivative, the Laplacian of 1 over r is 0. This is a well-known property. You can do it on more complicated combinations involving the two bodies, y1 and y2. You can then use the command simplifying scalar products and arrange things a bit. You can do that on this logarithmic kernel, and the result can be further simplified with factor, and it's well known. So it's a very good check. You have time derivative. The 0 here just specifies the Newtonian, post-Newtonian order. Here, it does not play any role, but for the derivative of the velocity, you need to say that the acceleration is the Newtonian acceleration or the post-Newtonian acceleration or whatever. Here, this is the 3pn acceleration involving this number of terms, and then you can differentiate it 2 times. So I try to do it. And you will find that the number of terms here is 541 after simplification. Very good. It's also useful sometimes to have time differentiation without replacement of acceleration. Now I think I will skip volume integration, but I have commands performing 3D integration and regularizing the results. Instead, I will go directly to this part because I would like to show you some ideas about how to apply replacements. So I have complicated potentials, and to replace them, I design rules that depend on the post-Newtonian order. So there will be a rule for order 0, 1, 2, 3, and I truncate at each order. So the rules are already evaluated. They are not re-evaluated each time you apply them. This accelerates a lot the replacement process. But of course, the first time you evaluate this cell, if you replace V by its value at Newtonian order, you find this very simple result. If you replace it at 3pn order, you will find, when the evaluation will arrive there, you will find something much longer. And finally, if I replace by an order which is too high, which is not known yet, you find nothing special to avoid mistakes. Okay, so now I just want to show you the mass here can be replaced by its value, okay, which is computed here in this cell from the potential. And now here I did, fantastic, wonderful. So I was not lying, as you can see. So I could compute this rule for mu1, and I find this mu1. Then I compute the source. These are the components of the stress energy tensor in the case of point particles. Mu tilde was just computed in terms of the potential. So now this is the source of the potential V. And therefore, you can integrate this source using the rule for mu. And I have a command to compute retarded integrals and truncate. And actually, I can recover the potential V because this source is precisely the source of potential V. So V was needed to compute this mu tilde in the source of V, but only at 2pn order. And here I computed V at 3pn order. When you proceed iteratively, you can compute at higher and higher order. But here you will find something with 1000 terms, not very long yet, but it starts to be a bit longer. It's still not exactly the same as the V that was loaded at the beginning of this session, but the difference can be computed, and it is just due to the fact that I neglected odd contributions in powers of 1 over c in the V I have loaded. So it just proves that I really recomputed something and not just computed the same thing. I mean, faked when computed it. So a few words to end with about large expressions. So the R potential is a longer potential but more complicated also. So if I replace R by its value, so it takes a very short time, so it's fine. If I expand the result, it's also reasonably fast, except tonight. But now if I use index rule for this replacement, it is much slower. You see 6 seconds, so it's 3 times slower than when I executed it this afternoon before. And if I try to expand this result, it takes this amount of time. I will not even try. So now I use this change expand command that freezes all symbols of the expression. So this prevents xTensor to try to do things during the evaluation. And now the expansion takes a few seconds. It will be longer tonight, but it's still manageable. And another way to do the same would be to avoid screen dollar indices, but this is still longer than the previous solution. I will not even try to apply my derivative x because of the dollar indices appearing in this differentiation is quite long. It is shorter if you map the result. So I have a map derivative x command to do that actually. Then if I have a large source depending on my potentials, I can try to replace the potentials there. So for instance, this is the compact part, and I just showed you before the non-compact part of the source. The compact part means that this is the stress energy tensor. I can show you the result. So the result is that if I load this after replacement, I obtain something which is very large, and the evaluation of this with arrange with two canonical is very long. And so I think you have to be clever in this case, check that the metric does not appear in the expression, that the expression structure allows you to skip two canonical, and that you can use two canonical only. So for me, xAct xTensor offers all the tools for the state of the art in perturbation theory and very high order post-Newtonian theory, and also post-Minkowskian theory. It is well adapted to manipulate multiple moments efficiently with high number of indices. The basic xTensor commands allow to design more elaborate commands tuned to the considered problem. So it is better to really tune the commands to the problem. And I find that for very large expressions, two canonical contract metric are powerful, but should be used only when strictly necessary. And dollar indices, they create problems in rules, definition, and scalar. And so we should find ways to avoid them if possible.
Great. Thank you so much. This is a really difficult area, and I've always been amazed by the performance here. So thank you very much, Guillaume.